same thing I'm saying here. So basically, I should be recording the voice chat. No, there's the recording. Let me start a new voice chat. Yep, there's now recording my voice. That means the other one's still recording my voice. Yes. So there should be two voice recorders. Nope, this is not a new one. So I get a new what I call it here. So basically, this video is on quantum computing, but I've got the formal version here for QRIFT. Basically, the C matcha string, but it's basically for the RIFT stage 3, 2 for RIFT stage 4. 0 is again the stage 0 is neo state is Alexa, which is the stage 1. Stable Alexa, 8 Alexa, and the stage 2 is the parser. If you go to the RIFT project is at GitHub. Basically, it's here. We're going to talk about this project here, but we got a lot of diagrams for me to show you, but I don't want to dwell on. So we got to show you here, and that's the diagrams here are here. So you got a lot of images to see, guys. It's not really got a lot of PNGs, but I want you guys to look at this models for dimensioning classes. But this is a dimensional conflict resolution. So you got EL, ER. Basically, EL is left rotated, R is right rotation. But these are rotation based on polarity. So you got the rift space. You get X is an input of dimension. So you got X an input, E is an linear cycle, and E sub L is the epsilon the rotation of X to Y, which is non-canonical, with some axis shift for polarity. So basically, when you put the R syntax, you get some kind of iota state, some kind of equilibrium state, where there's no one uses that space at a time. But that's kind of state. So that's what I'm saying. So Harvard space. You can look at these diagrams here. You don't have to hear all I say here, but you got all these diagrams you can look at any one point in time. Input stream, coding space, apply. It's if you go to the articles, you can give you this tools to look at it. You got the memory, you got sparse encoding. No, symbol X, sparse encoding L. But basically you go to the articles here, but this is just the way you can do it without broken codes. Can go to the transformation. Input X, transform T, rotation P, parallel pi. But you get for quadrant orders. Basically, if you have a transformation function, translation TK, you can put iteration. Basically, it's transformation in geometric space rotation within our geometric system of what lattice looks like. For each functor, there's a polarization, rotation, translation, enlargement, and polarization. Basically, you're just something instruction name. That's it. Yeah. So in element is just kind of go. For example, you go enlargement here, but it's not here. You get enlargement because enlargement is like if you can scale up, you scale down based on half flow. But you can do the same for the rotation. You can basically have this kind of rotation across all the dimensions of Cartesian and polar models, or something that's bridge and fluid for dynamic systems. So the goal is here this video is for me to explore this with you. So basically, I've got to tell you guys. So basically, RIFT is a flexible translator. It's a project I'm trying to work with for PhD computer. We do talk about the sixth approach, to be single command instruction like add to program task. How programs write load programs to load data versus W6 So basically, risk is like a first load command. Basically, what is I do like risk for evolution because everything's polyglot, but a sys complex is basically it's a single command. So if you type in that word add, you define two programs that add but this is like a duality problem because there's some kind of substrate that's shared between risk and Swiss architectures, and that's what I'm trying to do. Basically, I'm trying to build my own architecture language for this model, basically quantum computers. You don't because these one is quantum computers. It's going to be some quantum computers. So basically, when I do risk, I want it to be risk first because we're allowed to load stuff, but we know it's a very polyglottic interface. But the limitations of this is that risk is now the canonical add this is kind of off, and our add will not be the future add, so we have to have some kind of binding, but that already solved. Basically, we don't want to add some kind of overhead polygon library. There's no point of doing that because we're just handling architecture. So basically, the thing is like if you have no effect, if you have no cause, if you have no reason to do something, know how to what, how to why, how to when, how to do. You don't if you separate this how to from the why, the 5 whys, you really got because the how is the architecture. So when someone asks have to basically it's when you want them to just ask, you want them to ask how. When they have how they have the course. So basically you want them to do how they want, how to what, give structure or syntax. So I'm gonna write an assembly language in Rift stage 1 to ensure that the Rift how is preserved. So this assembly language is gonna be only Rift on. It's not gonna be independent from Gossilang. It's not gonna be Gossilang in new shape form. Anybody tell me nonsense in my business, I'll sue them. So basically, you're gonna have Rift as a core foundation of building any new tools. But then you're gonna have Gossilang, the world's first Pokemon with this. You're gonna have the other one branch out from Rift, which is not Gossilang. You're gonna have an assembly language from Rift Stage 3, Rift 3, 2, 2 to 2. So Rift 2 to 2. Stage 1 is Lexa. Stage 2 is Parser. Stage 1 is stage 0 is Lexa. Stage 1 is Parser or 1-1. Stage 2 is assembly. Is AST. So from AST and 2 to 3, which is like the epsilon state of E3, you get the assembly. So basically, Rift stage the 3 libraries, 2 to 2, will be using as the IOTA state to write 3, but it doesn't mean to go to 1-1-1 first. So basically, Rift is a Fluff translator. You can go to the Rift repository, but you have to match the basically matching the structure of this other canonical functors on the fly. Basically, it's a really it's like if you know what is just-in-time compiler. Basically, what the Rift assembly ecosystem is it's like a JIT. It's not a JIT. Basically, it's not just basically it's interpreting compiler. It's like it's a Rifty compiler. It's basically it's interpreted. Basically, it's not just in time you compile because that means you have to basically you interpret. So you compile first. When you compile, you then interpret for the architecture. So we want to make sure that we get to so basically the compiled Rift 3 stage 2 be written the compiler with compiler stage, which it allows you to bridge to Rift 3. But we want you to just write what you need. So the architecture of Rift 3 is just assembly components. Now gives you how you want to organize the latent memory. For what device you're modeling, maybe it's a sleep machine which I want to build. A sleep machine, so you get the model is to get R:33. Rift 3 is very important for assembly, but this assembly has an IoT interface, and that's from basically you're gonna have to ensure this unit can be decoupled at all stages. Basically, the code is a priority because if I do Rift 2 and then I it's gonna bad practice because Rift 3, and then I have a dependency, and then you have Rift 3 to something else that reaches Rift 3. It starts to couple. So have to decouple origin at all the Sparse model. But Risk is more personal. I love Risk. I love Sisk. But the term add is too rigid, so I don't like that term add. You can say we can define something that, so add, the word add is not going to be encoded into the system. It's more a reference pointer to the whole operation of adding, which we call the function. So it's basically I'm going to give you the definitions of the thing we're trying to do today. Let me just try to get it down more fully. So let me try to give you some Python code. So pseudocode in Python, some Python. So define def. So basically, you have something called a caller function. Callee is one being called, and the caller is a thing called the function. So you get def caller, and then you get some property to callee, the thing being called, which is just the next pointer. Basically, if you want to really model this, you get like a request response next, but it's like a routing service. So if I have the caller then can call as access to all the properties, of the callee, because it spawns. Basically, it's a function spawning. So the caller spawns the callee. So the caller says call. Basically, it can be anyway. The caller can have it as a policy, like at caller dot call callee. But it's best to invert it, because so you can call the, you just have to think about the callee. So it's basically caller def caller. And then you can run the function callee. Now basically caller. So basically caller the call. So def caller will have an input x y z, and then x y z caller will have the call caller the call. So basically you got so say it's basically let me just try to do it properly. So callee. So can you put the caller dot xyz? So you get the function. Now you find some so x is a variable and y is a variable, and they have some input x equals to caller dot call next callee. No. Okay. Now I got it, guys. Okay, so let me do it properly now. So get a def caller. We get the input request response. We get error request response next, because it's routing. So we get the caller error request response, and then we get the request is the input error, but they are sparse. You can have it as error request response, or you can have it as error request error response, or you can have a tuple. So you have three inputs. You have four inputs you can take. You have error, or error or result, and you get error or error request response. You get error request response next. Yeah, so this is the caller. So the caller is there. So you get caller error request response next. So this is what I'm saying. So this is the four type of input. It supports based on the input. So these are just inputs. So now you have the XYZ. So the XYZ axis. So if you only can spawn 3 at a time. Why? So the caller is the callee, the default callee. So this iota callee is can put it as IJK. But if I have IJK, I have 3 dimensions. So the current pointer to I is X. The pointer X, the type C, if I point to I, point to in, because you're mapping them homogeneously. So IJK is the canonical homogeneous indexing, like numbers, numeric indexing. You get the KXYZ, which can represent structured indexing queries from mapping for tridirectional consistence. So so we can define it. So we can do X, we do basically x basically by this basically x equals if x is an axis, x equals self like this function self which is the self dot core. Okay, self the yield. Now the yield is just basically the first yield. Basically this is now basically x is now. If I put x as yield, I'm pausing. I'm waiting for some kind of state to occur. I don't basically x is basically I'm trying to define this as a fundamental. So if I yield in this state, I'm saying that I want to yield some input. So after inputs, if I just pause, but this is like a generator pause. But basically this pause is sequence. This pausing is a sequence to a generator yielding. So it's pausing and it's waiting for some kind of data packet or something to signal something. But it's not indefinitely waiting. It's meant to like basically it's a observer consumer model for async modeling. So it's not it can be an async function, but the yield you got to yield star. Now yield star is yield all inputs. So that'll be request what it is via the iterable. So you can either the iterable itself or the iterator. So if I yield the iterator, that'll be yield star. If I yield the iterable, that'll be the IDK indexing all the in the list one by one. That'll be so x contains if I don't resume x, I then get x the iterables are just a list. But you know, if x is paused, it has to be gated. Let's wait something. So you get x, y, z. So if I get x, y, I can do x, y as a tuple equals yield some inputs resource. So if x, y is a vector, you can get s, y. You can compute for z. So compute for z. So when you're using x, y, when you're working with x, y, you're using them simultaneously. You get x, which is for 1, and y for 2. So what I'm trying to do is to focus. You get 2 states you're observing at a time. So so if I want to call the next function the callee, x is a state substate of the callee. So x can be paused, resumed, and continued because the call routine. So that's the pause, resumed, pause and resume. So that's the idea. So if x, this is so I'm going to define a chemical state for D. So if x is some kind of state, x of alerium E has some kind of x of U, x of Eulerian cycle and Hamiltonian, that chemical states if you're doing operations. So the goal of this is to have 2 sparse models. So if you have a node, if you have a node in the system, you have something that can move, that can go to something and back, but can go 2 ways. It doesn't basically it's tripartite, but it doesn't consist. You need consent, but it doesn't consensus to do it. So for example, a node can be something with a weight. Something can be like some kind of input, vector input that has to go through 2 channels, like a vector input, like for some one kind of lattice function. So you have a vector, say like 2, 3. So basically, this will go now for guys. Yeah. So you see this here, guys. This will annoy me. Guys, this will annoy me guys. So you don't even know half of it. So let me just size it down. So you see this. So basically, this is here. So this. So this is like a xy. So xy, x self that x xy is equals x or y is a tuple of a class data can be written on pause via intervals. But that's all stuff for now. Because I'm trying to give you the full overview now. So why do any of this? Why do any of it? Basically, the caller can call the consumer, and the consumer can call the caller. It is what it is. The caller can call the consumer, and the caller can call the caller. So basically, it's a sparse graph. So it's here. It's meant to be here. So you get the sparse graph here. So get so basically, when you have a state, one state, it can be in one state. It can be in 2 states. So if you're one state, if you're measuring one state, I'm trying to get 2 states in the class system. But it's already there in the quantum system. So there's 2 states. So I'm only observing 2 states. So if I'm measuring one state, I am someone else is measuring two states in an reality. So we have to measure. So if I'm measuring one state, there's two states to measure. Especially if I'm measuring one state, there's two states to measure. If I'm measuring two paths, two 111 paths, one. If I'm measuring 111 path, basically there's two. If I'm measuring two 11 paths for travel, there's four paths in total. There's four 11 paths that I have to use a smaller algorithm to do based on how I approach the problem. And what I'm doing bottom mouse button. If there's four 11 parts, there's another four Hamiltonian parts, making it of eight parts total. Etc. Everything goes to the power of n. When n is the linear time bound. So try to scale this to n squared. So basically your n squared computation is this classical equivalent of 2n, 2n invariant. They could be solved at no time. Just remove the n squared thing. So that's right here. There. So what else? So it's not a. So it's meant to be a star. So get a star 11, a star 11 function dy. So I've got the version here. I just gotta get it here. So I got it here. Just can't get the image here. Is it here? I got it. I don't really know. I don't really know actually. Oh yes, it is here. So I'm trying to show you guys why this really matters to me. For RIFT, basically the RIFT test based tomographic. It works on like measuring areas. Basically you test the area of the system. So you can sparse model. So you get a sparse model of the complex. So you can use that to match all the states because you just have to. Basically, you can just flip this one. Basically, you don't really have tomography. Tomography is measuring area. So you use the parameter what you know about the surface area to give you the density of a dimension. So, for example, in the RIFT matching, so you have like so basically you're gonna take the flags and use that to match your test because that's the better thing. So there's one-to-one connectivity. So you take the global, G for global, I for sensitive, T for top-down, B for bottom-up, all those flags based on architecture, and do sort from. But because there's a solution to it there. So what was I? So you see this, basically I'm trying to define some kind of a basically I've got my notes here. So basically I'm trying to find some kind of what I call a signature. Because the Python keyword and I know because the already language there that I'm used for a problem. So in a nutshell, you got the fn keyword, which stands for function in Rust, which is the same thing as a def keyword in Python. So fn and def are both what I call signatures. So basically, if the token of this value, there, the fn keyword is a Rust-bound signature for a function. So and the def keyword. Now, if you have the full system, get fn main, which is like the token type, the function main, which is the same thing as def fn main with Python colon and right bracket syntax, and that's right brackets. So these are two definitions. This is signature. So the thing you're gonna do is to just pick up encoding signatures. So the interpretation of the system doesn't look here over functors. So basically a canonical functor can be defined by the specification. Because the specification of the language is the target, can determine the target binary, which is just if you go to this SAM, if you do this SAM in Python, you have the SAM in Rust. So this assembler, this SAM model, if you import this SAM, you're importing this SAM assembler. But if you have some kind of if you have a binary shared linkable first and executable finite that doesn't understand some kind of encoding for function or functor mapping of functions, it starts to, it doesn't understand how the function build how the logic, not the data, based on statements, which is true or false, expression, the model of the data, of the next state, dynamic or static, and intent, the action to do or build. Because assembly is a architectural language, so it has to do something. It doesn't need to run a code. It just does. Basically, the architecture is silicon, so this must be sure that it's not rigid tomographically, which I'm trying to say. So I go with example here. So basically, intent is like the program's job or task, or like a child process. What it's meant to do. What's it meant to act on, what it's meant to consume, and observe. What's it meant to do for that set state. So you get that here. So you get the problem here. So we got it here for you guys. So let me get my encoding table now. So this encoding table here. So she's like a A to Z. So this is asking questions, but I love asking guys. You gotta understand this thing. There's no glue on glue here. It's just all glue. That's the close. In Gaussian, because it's all glue. So I got the letters A to Z. Small a to small z. But that means you can start. Basically, basically if you start from A to Z, that's what you're starting. But someone can start from like some letter. So basically, 25 divided by 2, because 25 divided by 2, 12 letter, that's L. That's A, B, C. So I'm not trying to do it. So you get basically the first letter to the fifth letter, and in between are all starting points, based on centrality. 1 to the 5. I don't know why you're looking at me. I don't do anything to you. Go to Jordan. Stop this, man. I don't give shit. I'm busy. I don't give a shit. So, I don't care, man. So you get a letter L. 12 letter of the English alphabet. 12 letter English. Finish now. Finish when I do finish this video. Don't disturb me. Don't disturb me, please. Please don't disturb me. I'm busy. No, you don't. No. I don't. 12 letter word. No, 12 letter English alphabet. It doesn't make sense to me. Basically, the 12 letter ABs. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's basically, if I start from A, that'll be K, A, K, 12. Now, 25 minus, then 25 divided by 2 is 12. So 12 is K. But then K will be L. So that'll be A, 25 divided by 2. So 25, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 will be K. So my 12 will be K, and their 12 will be O. So basically, when I'm seeing O, they're seeing K, or KO. And we go, oh, that rings a bell. That's perfect. So the idea is there's a canonical state, K and Z. Basically, 1 is the number 1 and 25 are start symbols, but the return state, but the end symbols are really central bound. So you get L, you get K, KO, OK. OK. Basically, KO represents some of state, based on how you model systems. So you get 1 to the 5, 1 or 12. You start from the first letter A, you get some transition to Z. From Z, you get some to A. But that's some pressure. If you get from K, you go to O. From O, you get to K. But this is the canonical A, so you get to. If I'm trying to go from A to L, and then or Z to L, that will be O to K, really, or and K to L, and really basically that's the only thing that stays the same, because because No. If I'm going to try and go from O to B, so if I can go from A to Z and Z to A and backwards, the only letters I need to stay in between are central K to O, which is the center point. So I can compute from 0 to 0 OK all of A to B because it's halfway based on geometry alignment. So you may understand where I'm going with this. But let's do this now. Basically, I'm gonna work on a problem, and I'm going to follow it here because I'm of clarity in the system. So yeah, you see this thing? Yeah, so my paper here. So go here. So basically, the problem is simple. A to Z is 97 in decimal to 122. Now, and 122 to 1997 other way around. So you get a one-way system. So you don't have the dual thing there, because dual thing just means you send information. So you don't want a dual thing, you want a singleton. So you have the minimal source you get. So you only get from small a, which is 97, or number 6, or actually decimal 61 to 7a. And you get from the number 122 to 97, which is 7a to 61. One way. Only it's only like no dual system must proceed, because if you're sending something, you may be receiving it. But this is a local system, so it's no need to duplicate the stream, bytes. Or use a duplicate stream. Who's what we do as a policy in this export framework. So it's an encoder system for like functors. I'm going to find here. So if I'm trying to go from A to L, I have 3 states I can go to. I have 3 A's. So from 3A, so I'm either, so basically, if I'm going from the letter A to, I can have A. I can use the Lorentz cycle, the Eulerian and Hamiltonian cycle, and have that A star score with some kind of invariant principle. So if I start from H and E, I have something they share, some share, and something that don't share, and one thing things don't share. I can use those things don't share to half my time, because or the speed, etc. That's what I'm trying to do. But some kind of teachers, listen, I'll come tell you one day, maybe I don't know. So idea is to give this as a state machine, which is sparse encoding. So that's the idea. Remember sparse encoding. So this is epsilon 3 true get triple try that is epsilon. Yeah, so I got it here. So this is so basically so basically this is a B. So this is the risk one. This is the risk one. Risk one. So you get A. So when I'm at state A, I'm looking, I already know state. I already know, because I'm looking at it. I know it's. I already know states B and L. So basically on some algorithm. So the edge band algorithm is 11, but it's a Hamiltonian Cisco graph. So Hamiltonian Cisco 0 Cisco. So if I know A, I'm currently at start A. I'm looking at COK as state. Based on Risco DFS, basically I'm looking at B and then if I'm already polarized to B and A, I can get the information of B and A using kind of the opposite. So we can go to L, because if basically you don't I already know it because the information is already there, but I have to just align myself with the information based on some algorithm. So polarity. So now to basically get the first priority, the second priority graph, and you get A on the left, right A, you get B or L or B, and then right node C, okay. And then the second depth of the left row root B key, you get CD and JI, and then from JI you get JI. So JI is the end state of that. So if you go to CK, so CK is the next state. You get the first layer, and then you get the second layer, and then you get CA, and then you get HI, CK, and then you get HI. So IH. So CK gets HI. So true. So so get CK. So basically, you can define this as A if you get the opposite one, so this is just the C left with right. So it's a tree AVH a self-balancing tree for balanced states or data functions. So if A is a state, state, you can have the opposite. A is an edge. So it's homogeneous can be heterogeneous. A as a state is a state. So a state is so if I'm trying to get to L, A, B, C, D, I can go A because I go to Z. But if I'm already at L, if I know my point is L, I have to go through C, K, medium. So because C, K share the same state space for the encoding. So so this is the Hamiltonian graph. Let me just try to give it a final structure so we don't mess it up maybe. So here, so I'm looking at here. So if I'm gonna state A, I get basically I'm looking at all the B's. A. So I have a 2B, 2C, 2B, LL, 2C, actually the share encoding of 2C, JI, 2I, 2I, C, okay, 2B, 2C, 2I, the share, basically the left node share, basically the left node share I kind of consists of two C, two C and two I, and they don't share anything. Don't share K. They share K. They don't share K, KB, or I or H, which is just the non. Basically, there's no intersection here. So it's an intersection. So, but they do intersect at 2C, one each via Hamiltonian traversal. So for the Illyrian one, which is what I'm saying. So for the Illyrian one, it's like it's Illyrian one. So that's edge bound. So if I'm still going to I have this one. So this is Illyrian. This is edge bound. So it just flips everything. But, huh? Who you calling bastard?
Sorry?
You calling me bastard? Are you calling me a bastard?
What? What? Am I talking with you?
I don't know. Don't start this.
You said you were finishing, then why don't need to talk with you, yeah?
I don't care, Ibrahim.
No, you said you were finishing, so I don't need to read anything, yeah?
Don't start this, Ibrahim. So you get so A, H, I. C, okay, so AICK, and then that's the Hamiltonian one. You get AI, HI, which is the endpoint, 11, CK, and then you get 2A, so you get A or L. So they in the Illyrian graph, they share an A and L, but I'm not done as a lattice. A and L, and then a C and D, and then J and K. Is it J and I? No, J and God, J and I. So basically, basically, there's the same thing with the share. The first so basically, basically, if I use a Hamiltonian cycle, I polarize I have to sync my 2C or 1, 2, and 2I with a shared state, and then union states for lattice, and then you get the disjoint states, which is haven't done yet, but the union state of the Hamiltonian is K, and the disjoint is KBH. So the KBH has to unite somewhere. So so we get the Illyrian one, A. So from if I start with symbol A, I already know H and I, H. So because that's right root left. So if I start from A, I know CD. So I have 2C in Illyrian one, so Illyrian, and I share 2C, and I share 2C, and I share 2A. No, I share 2A. Let's keep 2A there, and then 2 share lines D, 2C, 2C, 2K, 2A, 2I. They show 2I, 2I across the out, and a H. They don't share a H in the left. Basically, you're looking for isometric between the left root and the right root, based on how well the root is. So if so basically in the right root, so basically in the right tree, basically in the right graph, which is not the right root, you can model this homogeneous as 2 right roots, which can share, basically keep everything as a function. So this function will define how it works. So for example, in the right root, for Eulerian graph, there is this kind of model. So you can see this picture number. So this is your work now. So basically, there's some kind of a risk 6 dilemma for duality for matches. So you get some kind of pure function, a mapping of pure functions and unpure functions. They need to discard. So you don't keep the unpure, because the unpure functions are noises, very noisy. So you have to keep them away. But keep all the things that are pure, because that's how the computer can encode the functions that it computes in real time via relay signals. So that's the idea that you are storing and encoding for RISC-2 as a isomorphic AVL tree in binary, of course. So get the binary code here. I'm not even done here. So choose this one, binary code. So for example, here you get A here. So you get 97. So you get so basically, if you get the letter 0, 1, 1, 0, 0, 0, 1, and you get this is 97 in decimal, you get 0, 1, 1, 0, 0, 0, 1, 0, and this is like B, B. So you get A, B, L, L, 0, 1, 0, 1, 1, 0. So basically, if you do the XOR, the O of A and B, left shift, you get 1, 0, 1 on the left, 1 on the right, 0, 0, 0, 1, 1, 0, and this is the O, A to B, O, O encoding. So this is O, and then you now get the XO. So you now get the XO table. The XO is like the thing you store. So you get the XO. So if you exclude 0, basically the last state. The last state, basically you do it twice. So you get A or B, but my target is L. So I have to do L. So now O, L. So you get A or B. So O, A, B, B. Now O, L. You get 0, 0 is 0, 1, 1, 1, 1, 0, 1, 1, 0. And this is a O, and then you get the O. So this is a XO, O, O, B, L, A. So basically the O encoding of this state at this time is O, B, L, A. So you see that? So basically, these are just binary encoding in ASCII. Oh, so now I get to store. So if I now do exclusive O, A, so I have to do invert A. So how do I invert A? So I have to do exclusive O, E, this state. So this is the last state. So I just do it once. So this, if I see a 1, I suppose 0. If I see a 1, I see 0, 0, 0, 0, 1, 0, 0, 1. So basically, the letter 1, 0, 0, 1, 0, 0, 0, 0, starting from the right, beginning from the right, as a symbol, which is left. Basically, if I do basically 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, is the left encoding, and you get the right encoding of the state. So you get that there. These people annoy me. So that number there is what yeah, so you get the hexadecimal. So if I type in the convert to binary, if I do exclusive OR, basically I can do the exclusive OR of all the states. But basically, if I do the exclusive OR, this is the exclusive OR of L, that would be the exclusive. I have to do exclusive OR X or L. How is it exclusive XL? So I could big L SM. Now do the exclusive OR of what? Of A, and that will be X sub A will be exclusive OR of A will be 1 0 0 1 1 1 0, and this is X B. This will be or this will be, oh, this is wrong. Oh, this is wrong. Sorry guys. This will be O3. So basically, you get all the states exclusive OR first. X sub B will be 1 0 0 1 0. Wait, 1 0 0 1 0 0 1 1 1 0 1, and X sub C will be X of L will be 1 0 0 1 0 1 0 0 1 0 0 1 1 0 0 1 0 0 1 1. So this is X B A B. So this is basically the states of the chemical states of the system, based on exclusive OR. Basically, they can all agree. So the XOR operation I've spoken, they can all agree they're here at this stage. Guys, keep it XLO. So this is XOR, basically X A B L. Basically, I'm trying to get to B L, which is the endpoint. A B to the number L, because just L is just random. That's encoding of it. So of them being in exclusive OR. But that's basically just a diagram. So which stands for directed instruction random memory. So if I have a state of that, I have another state of OR. So if I do OR, let me do it properly now. I'm not scared of anyone, by the way. So you get EXO, so you get EXO, so you get but you know, you get the O, so you get O. So if I do O of A and B, I go O, A, B, and I go O, B, L, and I got O, A, L, and I got O, A, B, L, A. So basically there is 4 states you have for this configuration. The functions are the states you get O, A, B, which will be again 10-15 minutes now. O, A, B will be 1 0 0 0 0 1 1 0 0 0 1 1, and this is O, A, B. O 0 1 1 0 0 0 1 1, and then O, B, L will be O 0 0 is 0, 1 and 1 is 1, 1 and 1 is 1, 0 0 0 0 1 1 is 1, and 1, oh sorry, BL. So BL will be 0 0 0, 1 and 1 is 1, 1 and 1 is 1, 0 0 is 0, 0 1 is 1, 1 and 0 1 is 1, 1 or 0 is 1, and 1 and 1 is 0. So you get BL, and then you get or AL. So or AL will be AL will be 0 0 0 1 1 1 or 1 is 1 1 1 0 1 1 0 1. So you get or AL, and you get what or LA. So LA will be 0 1 1 1 1 1 1 1. So So you get the four. You get 1, 2, 3, 4. So you get this state is stored. Don't step in a second. Just store it. You're gonna do this. You're gonna don't do this to me. So you get the system is there. There. Basically, it's measuring the it's basically this encoded state is stored by the computer. This encoded state get yeah, you get the encoded state 0101. But you get this one here. You get this one here. These are the canonical ones. So every transformation that shares Eulerian Hamiltonian graph should respect this encoding. Have it embedded so the system doesn't never as a canonical function to be computed for any transformation or region for the architecture for which 16. So this is like how the system works. There's no need to desync anything or sync anything if there's an equilibrium in the medium of canonical computation, and that's what I'm saying. There's no need to disassemble anything because the system, the signatures are the same. The interpretation means is uniform. It basically works on all systems. There's no it's polyglottic. I'm trying to show that you don't need to ever change a canonical symbol. That's you don't change the function definition ever in a language. You just change basically the Python understands the signals it's getting, but you're talking to Rust or C. You have the same function. You have a function in Rust speaking to C or C or Python or Lua interpreters. Interpreting language. The interpretation is just canonical to the language. There's no need for any abstraction, any new libraries, any new components, because as a policy, the system doesn't only listen to what it needs. So it basically listen to something, but it doesn't understand what that is. It just ignores it. It just doesn't. Basically, it just consumes by listening. That's Python. So if Python is listening, it just listens to what it knows. But what it doesn't know is just noise. So it just discards it. It doesn't need to take into account, because that information is not for the system of Python libraries or the Python ecosystem in any shape or form. That's the goal here. It's like when you consume in a polyglot system, you have to listen. When you listen, basically it's consumer bound to the GSF file in Gaussian. Thank you guys for watching.